The first thing we need to do when talking about a redox reaction is we need to be able to balance an equation for a redox reaction, all right? And some redox reactions have some special techniques that we need to talk about here real fast. In this little video, you have an iron and a permanganate. And when iron and permanganate come together, a reaction occurs. But the question is what happens and stuff like that. That's the kind of stuff we're going to look at in this chapter. Permanganate is MnO4 minus 1, and in the clear liquid, quote unquote, that's an iron plus 2 solution. And those react in a little bit of acid, which is what the H plus represents, to make manganese 2 plus, some iron 3 plus, and some water. If you remember oxidation numbers from Chemistry 221, the oxidation numbers will change in a redox reaction. Now, if it's a simple atom like the iron 2 plus there, the ionic charge equals the oxidation number. So that's easy. Manganese in MnO4 minus, to figure out its oxidation number, you need to remember that hydrogen's usually plus 1 and oxygen is usually negative 2. If there are 4 negative 2 oxygens, but the overall molecule has a charge of negative 1, that manganese must be a positive 7. So you can think about it like that positive 7 plus 4 times negative 2 from the oxygens, all of that equals negative 1. That's how you find out that this is a positive 7 manganese. And if you look on the other side, you'll see that both the iron and the manganese have changed. In this problem, the manganese is positive 2, the iron is plus 3. So the manganese has gone from a positive 7 to a positive 2, and the iron has gone from a positive 2 to a positive 3. Notice that the iron has become more positive. That's only possible if iron plus 2 has lost electrons. Iron plus 2 here is being oxidized. On the other hand, manganese has become less positive. It's gone from a positive 7 to a positive 2. And that can only happen if the manganese in permanganate is being reduced. These are the kind of things we're going to look at in this section.
The purple solution is aqueous potassium permanganate. The colorless solution contains iron 2 plus ions. When we combine them, a redox reaction occurs. The permanganate ion is reduced to manganese 2 plus, and the iron is oxidized to iron 3 plus ion.
Iron 3 plus has a very slight yellow color, so you can see that solution is not quite clear, but pretty close to it. But the purple permanganate is totally gone, and so you can quickly see that something has happened. Redox reactions are really powerful when they occur. In the companion and also online is what I call the redox reactions handout, and I do recommend that you check this out. It's going to go through the steps we're going to talk about in great detail, and you can see how to balance these redox reactions. None of these processes are hard, but you should follow them step by step, at least at first, to make sure you don't miss something. So check out that handout if you get a chance. Here's a good question. What's the oxidation number on the vanadium atom in VO2 plus 1? Okay, so metals are almost always positive numbers, so that's good. How you want to do this is remembering that hydrogen is plus 1 and oxygen negative 2 almost all the time. You can figure out what the mystery element is, and the mystery element here is certainly vanadium. The sum of all the oxidation numbers must equal the charge on the atom, if any, all right, or on the molecule. And in this case, what that means is that the oxidation number of vanadium plus the oxidation number of 2 oxygens equals positive 1. So oxygen's usually negative 2, and there's 2 of them, that's negative 4. So you can write, if you want, you can write the oxidation number of the vanadium plus 2 times negative 2 for the oxygens, and all of that equals positive 1. And again, the positive 1 just came right there from the charge. So you want to solve for OV, the oxidation number of vanadium. So OV minus 4 equals plus 1. Add 4 to both sides. You can see that that vanadium is a positive 5 vanadium. This is really handy. Once in a while, it will be helpful. And I am going to show you some techniques to kind of get away from this if you don't like using oxidation numbers, but it is all stuff that you can do.
Copper metal reacts spontaneously with a solution of silver nitrate. A coating of silver metal forms on the copper, while copper 2+ ions, which are blue in water, are released into the solution.
Let's start our balancing of redox reactions with a relatively chill example. This is copper metal reacting with silver ions to make copper 2+ ions and silver metal. Now, honestly, this is probably a redox reaction you could balance right now. Okay, it's not that difficult. But I want to go through the steps that will help us when the reactions do become more complicated. Then you will be good to go. If you're going to balance redox reactions and you want to do it the right way, first thing you want to do is you want to divide the reaction into the half reactions. One of them will be for oxidation and the other one will be for reduction. So in this particular example, that means you want to put the coppers together and the silvers together. Now, if you know which one is being oxidized and which one is reduced, awesome. But on the other hand, if you don't worry. We're going to see that later on it's all going to come out when you start putting electrons in. But as we talked about earlier, copper is becoming copper 2+. It's becoming more positive. That is the site of oxidation. On the other hand, silver plus going to silver 0, it's becoming less positive. That's definitely the site of reduction. Next thing you want to do is you want to balance each half reaction for mass. So you want to make sure that the atoms are balanced. And everything's already done here. You have one copper on each side and you have one silver on each side. So this one's not that exciting, but it will be later. Okay. Step 3, balance the half reaction for charge. And in order to balance for charge, the only thing you can do is add electrons. So if you look at the copper going to copper 2+, you have like a 0 charge on the reactant side and a positive 2 charge on the product side. Well, 0 is not equal to positive 2, so this is not balanced for charge. If the only thing we can do is add electrons, and remembering that each electron has a -1 charge, then for that oxidizing part, we want to add 2 electrons, because 2 -1 charges plus a positive 2, that all goes to 0. And that means the product side has the same charge as the reactant side. So this reaction is now balanced for mass and charge. Now, on the other one, the silver plus going to silver, remember the only thing we can do is add negative electrons. So we're going to add 1 negative electron to the silver plus side. Then we got a +1 silver and a -1 electron. They cancel out and go to 0. Now both of these reactions are balanced for charge. But remember, the only thing you can do is add negative electrons. You want to add negative electrons to the more positive side. On step 4, you want to multiply the half reaction in some ways to cancel out the electrons. In an overall balanced reaction, you don't want to show any electrons. So you can see in that those 2 half reactions from before, one of them had 2 electrons and the other one only had 1 electron. If we were to add those reactions as is, there would still be an electron left over. And in chemistry, no showing of electrons. So we're going to multiply the silver one by 2. We're going to leave the copper one alone, but we are going to multiply the silver by 2, and we're going to do the whole thing. And we do that because now we have 2 electrons on the product side for copper and 2 electrons on the reactant side for the silver. Because, you guessed it, the final step, add the 2 half reactions together. And if you've done this right, this step won't have any electrons. If you do this, copper plus 2 silver plus makes copper 2+ plus 2 silvers. Bam! First balanced redox reaction under our belt. We're good to go. If you follow these steps through, you'll be totally fine. If you don't follow them through, of course, there could be some issues. You can always double check yourself if you're uncertain if you've balanced it correctly, because the final balanced reaction should be balanced for both charge and mass. And this reaction is balanced for both. It's got a copper atom on both sides and 2 silver atoms on both sides. That's the mass balancing. But it should also be balanced for charge. Now, copper metal has no charge, but 2 silver pluses means +2. So the reactant side has a +2 2 charge. On the product side, we ignore the 2 silvers because they have no charges now, but there's a positive 2 on the copper. So the product side has an overall positive 2. Positive 2 on the left, positive 2 on the right. Bam, we are balanced for charge, and we already saw we're balanced for mass. This is a great equation. So these steps, none of them are crazy, all right? You just kind of got to go through them. There's a few of them, but once you do it a few times, honestly, it's pretty easy. The next example is going to use that vanadium complex we talked about earlier, the VO2+. Vanadium is named after the Swedish goddess of beauty, apparently, and that's the case because vanadium makes a whole bunch of really awesome colors. And these are just examples I saw from a picture. Vanadium can make that yellow on the left. It makes blue, green, and purple, and some other kind of colors. It's a pretty cool kind of element. I love the colors of metals, like I think I've told you before. Anyway, so that's why I get so excited by it. But anyway, we want to balance this reaction in an acidic solution. And this reaction has VO2 plus 1 plus zinc, and it's going to VO2 plus zinc 2 plus. So these aren't quite as common species, so they may look a little bit different. And also we're throwing in the idea that this is in an acidic solution, and that'll be important to us too. But if you follow those steps we went through earlier, all of this is going to do really great. So the steps before, first thing you want to do is split up the 2 half reactions. And if you don't know which is oxidized and reduced, it's no big deal. But splitting them up, then you're going to have the 2 vanadium species together and the 2 zinc species. Now, zinc going to zinc 2 plus, zinc 2 plus is more positive. Zinc is definitely losing electrons, is being oxidized. It's harder to know on the vanadium. By default, hopefully vanadium is a reduction because in a balanced redox reaction, you need to have something being oxidized and something being reduced. You can confirm that it's reduced by looking at the oxidation numbers. So we saw earlier that V and VO2 plus 1 is a positive 5 vanadium. VO2 plus, we can do the same kind of process we did to figure out it was vanadium. The other one was vanadium plus 5. Vanadium, which is unknown, plus negative 2 for the oxygen equals positive 2. If you put the negative 2 on the other side, it becomes positive 2. That's a positive 4 vanadium center. The next thing we need to do is we need to make sure everything is balanced for mass. Now the zinc is easy because it's only 1 zinc on the left, 1 zinc on the right, good to go. But the reduction part with the vanadiums, those are not balanced for mass. You have 2 oxygens on the left and only 1 oxygen on the right. It becomes really important to pay attention to the pH of the solution. This is under acidic conditions. So in an acid, you want to add H plus and water only. So for this one, we're first going to add a water molecule to the product side because initially we have the 2 oxygens on the left and only 1 oxygen on the right. By adding a water, now the oxygens are balanced. That's cool. But as you can probably tell, by adding water, now we've got some hydrogen ions running around. We have to take those into account too. So if you add 2 H plus to the reactant side, which is also allowed if something is acidic, now we have a balanced reaction. So if you have acidic solutions, all right, you add water to the oxygen deficient side and you add H plus to the opposite side. In an acid solution, you can only add H plus and water. Don't add anything else, all right? That becomes really important. So in this problem, we added H plus to the left side, water to the right side, and now everything is balanced. You can always stop and check yourself too. So in this last example, we had 2H plus on the reactant side and 2H plus on the product side. 1 vanadium, 2 oxygens. Well, 1 oxygen is here and the other oxygen is there. This reaction is balanced. We're good to go. The next step, balance the half reactions for charge. And this is the step when you can only add negative electrons. You can't add anything else. So in this reaction, again, the zinc is pretty easy. Zinc going to zinc 2 plus. Zinc 2 plus is more positive than zinc. We're going to add 2 negative electrons to the product side. And if you look at it now, the product side has positive 2 plus negative 2, overall 0 charge. That's what the reactant zinc has. This reaction balanced for charge. Now for vanadium, it's a little crazier, but if you look on the product side, there's an overall positive 2 from the VO2 plus. And ignoring the electron for a second, VO2 plus 1 is a plus 1 atom, and the hydrogens each have a positive 1. So the positive 2 from the hydrogens plus the 1 from the VO2 plus 1, that's positive 3. And that's more positive than the VO2 plus side with its positive 2. So we're going to add 1 electron to that side, negative 1 electron plus 2 from the hydrogen plus 1 from the vanadium. That comes out to be an overall positive 2 charge. And on the product side, that's what we have there too, positive 2, so we're good to go. Now, the next step is we need to multiply the half reactions in such a way so that the electrons will cancel. And again, zinc is being really good. We don't have to do anything to zinc. Zinc's pretty boring. It has 2 electrons in it. But obviously, the other side with the vanadium, we're going to have to multiply everything through by 2. Again, the goal in the next step, we're going to combine the half reactions so that the overall thing doesn't show any electrons. So we're going to multiply everything through by 2 electrons plus 4H plus 2 VO2 plus 1s, and that makes 2 VO2 pluses plus 2 waters. Again, you multiply everything through by 2. And then finally, the last step, arguably the fun step, add everything together, and those electrons had better cancel out. And if you do that, you can see that the 2 electrons on the product side there cancel 2 electrons on the reactant side. You're left with zinc plus 4H plus 2 VO2 plus makes zinc 2 plus 2 VO2 plus 2 waters. And again, at this point, you're welcome to go back and balance the reaction. Make sure that everything's balanced for mass and charge. I guarantee it is and stuff. You're good to go. This is how to balance reactions. Now remember, this was an acid solution. And in acid solutions, you can only add H plus and water. You don't want to add anything else to these. For acids, just H plus and water. In this question, it asks how many electrons flow between the tin and the silver plus. This will be something that we'll talk about more later. And again, like a lot of these problems, there's multiple ways to do this, okay? What I would do on a problem like that is look at the tin on the left and the tin on the right. And you can see that tin is a 0 on the left and tin is a positive 2 on the product side. Well, it can only become positive 2 if it has lost 2 electrons. So let's tentatively say the answer C is right. But you can also do this from the silver's perspective. Silver plus is going to silver. So silver plus must gain an electron to become silver. But notice the 2 right there. You need you need 2 electrons to combine with 2 positive 1 silvers to make 2 silver metals. So there's a factor of 2 going on. Tin is losing 2 electrons, and because of that big stoichiometry of 2, the silver pluses are gaining 2 electrons. 2 silver pluses are gaining 2 electrons to become 2 silvers. So any way you look at it, this is going to be a 2 electron transfer. If you wrote these as half reactions, you'd see tin goes to tin 2 plus 2 electrons. You could also see that 2 silver plus 2 electrons makes 2 silver. These 2 reactions here are both balanced for charge. If you have a reaction that's balanced for charge, you're good to go. But this does actually bring up a different way you could do it. If you just looked at tin going to tin 2 plus and you balance for charge, well, this tin has no charge, this tin has a positive 2, you would have to add 2 negative electrons. Remember, you can only add negative electrons to balance for charge. And you could do the same kind of thing with the silver ions. So by hook or by crook, it is useful to know how many electrons are flowing between the site of oxidation and the site of reduction.